Hello friends, welcome back to this series where we go through and explain the book on quantum mechanics by Steven Weinberg. We are now at part 11 of chapter 2 on a particle in central potentials. Today we move on to a different potential which defines a quantum harmonic oscillator. In this model, a mass m is anchored to a point by a spring, but is otherwise free to move in three-dimensional space. The spring constant k can be written as m times omega squared, where omega is a new parameter to replace k. This choice of symbol is deliberate, as omega will turn out to be the angular frequency of the oscillation. The Hamiltonian of this system is familiar from classical mechanics, with the potential given by. Let's expand out this Hamiltonian in components form. We find that it can be written as a sum of three terms, corresponding to three independent spatial directions. This independence is expressed mathematically by the following canonical commutation relations. Variables associated with different spatial directions simply commutes. Therefore, it makes sense for us to first study just one component of the motion, then extend the results to three dimensions, which should be quite straightforward since all three components have identical Hamiltonians. Let's do some dimensional analysis and check if omega could really be a frequency. H is energy, while x squared is length squared, so m omega squared should be energy times inverse length squared, which means omega squared has the dimension. We also know that kinetic energy is mass times velocity squared. Substituting this energy into omega squared, indeed, omega has the dimension of frequency. The Hamiltonian can be written as the sum of two squares. If these were just ordinary numbers, we could immediately write this as the product of a complex number with its complex conjugate. But we are dealing with operators, so care must be taken with operator ordering. This results in the last term, which is the difference between two opposite orderings. The last equality is not yet true, but let's apply the green box to the blue box and see if we could make it true. Let's work out the commutator term for the blue box. It would be convenient to write the constant prefactor up front. These are terms in the red boxes associated with the cross terms of the product. This is because only x and p has a non-zero commutator. So we must subtract away this commutator term in the red box to make the last equality true. The commutator term is just a number. H bar omega has the dimension of energy. Let's make this the prefactor of the Hamiltonian, so that we only have to deal with dimensionless operators. And indeed, we end up with a product of two dimensionless operators that are Hermitian conjugates of each other. These are called ladder operators, which we shall explain in a moment. A is known as the lowering operator, and A dagger the raising operator. This formalism is yet another clever idea conceived by Dirac. At this point, we essentially have the entire set of eigenvalues and eigenvectors of H. All we need is the commutation relations between A and A dagger, as we shall see. This commutator is only dependent on the commutator between X and P, since the rest are all zero. The associated coefficient is as follows. The minus sign comes from the difference in relative signs between X and P. But this can be absorbed by reversing the order in the second commutator. We shall now use this relation to derive the eigenvalues and eigenstates of H. More precisely, we shall do this for the operator A dagger A, which is called the number operator, because its eigenvalues turn out to be all the counting numbers. This is a Hermitian operator which obviously shares the same set of eigenvalues with H, with a one-to-one correspondence between their eigenstates. Let's expand out the commutator. Multiply by A from the left on both sides of this equation. Now apply the operators on both sides of this equation on the eigenvectors of the number operator. At this point, n is not assumed to be a positive integer. On the left-hand side, we can apply the equation in the yellow box. Here, we can see that the effect of the operator A on the eigenstate n is to generate another eigenstate with eigenvalue reduced by 1. This is why A is known as the lowering operator. We now show why A dagger is the raising operator, using again the commutation relation. Applying A dagger on both sides of this equation. And again, applying this to the eigenstate n. This shows that A dagger raises the state n to a state n plus 1, which has an eigenvalue increased by 1. That's why it is called a raising operator. We now show that the eigenvalues of the number operator are all the positive integers. Applying bra n from the left on both sides of this equation, and assuming that the states n to be normalized. Writing an as some ket phi. We can write the left-hand side in the form of an inner product of the ket phi with itself. This has to be greater or equal to 0. This means n will also satisfy the same inequality. Therefore, the smallest possible value n could have is 0. And this can happen only if the vector phi is 0. This corresponds to the condition where A acting on the eigenstate with eigenvalue 0 equals to 0. Suppose we take an arbitrary eigenvector of the number operator with eigenvalue lambda. We could keep on applying the lowering operator on this state to get eigenstates with lower and lower eigenvalues. This process will only terminate when we reach a null vector, which is invalid as a state. Let's assume that it takes n+1 applications of A for us to reach this stage for this particular state lambda. And we notice that this state is precisely one of those states with the smallest eigenvalue 0, because it satisfies the condition in the green box. This already tells us that the eigenvalue lambda is in fact equal to n. Since lambda is any arbitrary eigenstate of the number operator, this means all its eigenvalues are positive integers. This is the origin for the name number operator. We now want to check if this condition, which any eigenvector with the smallest eigenvalue must satisfy, gives us a unique ground state. Let's project this equation into position space and see what wave functions it would give. Substitute in the expression of A in terms of x and p from earlier, because we know how these operators act on the position state. And we end up with a first-order differential equation. This has only one constant of integration, which would be fixed by the normalization condition. Thus, we have shown that the condition in the green box does indeed give a unique solution for the ground state. Let's solve for the ground state wave function psi 0. This equation is easily satisfied by the Gaussian function, which is a normalizable wave function. We will now show that the tower of states, consisting of applying the raising operator any number of times to the unique ground state, gives us the entire set of eigenvectors of the number operator. That is, any arbitrary eigenstate lambda of the number operator can be expressed by the following for some power n. Here's the proof. One thing we can be sure is that we cannot descend from the state lambda for an infinite number of steps. That is, after applying A some n+1 times, where n is non-negative, we must reach 0. This is of course the same as applying A to the ground state. Here it is useful to look at the following general relation, in which descending from an eigenstate psi, we reach another eigenstate psi prime. The question is, could we invert this equation and express psi in terms of psi prime instead? Let's try by applying A dagger to both sides of the equation. On the left-hand side of this equation, we have the number operator acting on psi, which gives the corresponding eigenvalue n psi. Dividing by n psi completes the inversion. Of course, we have assumed that psi is not the ground state, so that n psi is not 0, making this division possible. Thus, psi is just proportional to A dagger psi prime. It would be convenient to work out the normalization of this state. Taking the inner product of A dagger psi prime with itself, we have this evaluates to The term in the bracket is just the eigenvalue of psi. Here, we shall assume that the state psi prime is normalized. So the inner product of A dagger psi prime is n psi. This means if we want the state psi to be normalized, we need to pair the vector A dagger psi prime with a factor of 1 over the square root of n psi. Let's get back to the proof of the relation above. This equation implies that the two terms in the red boxes are equal. We can invert this equation to express the state lambda in terms of the ground state by applying the inversion in the yellow box n times. Thus, we have proved that any eigenstate of the number operator can be reached by applying the raising operator on the unique ground state for some number of times. The relation in the yellow box below allows us to normalize these states if the ground state itself is normalized. We do this recursively, as this simple example demonstrates. The pattern seen in the red box is obviously quite general, and is the result of applying the relation in the yellow box 3 times. The arbitrary state is given in the blue box, which is the generic form of all the eigenstates of the number operator. The yellow box ensures that these states are all normalized, as long as the ground state is normalized. We can write the yellow box in terms of the notation of the blue box. This gives the effect of applying A dagger to the normalized eigenstate n. To get the effect of applying A instead, multiply both sides of this equation by A from the left. Again, we can apply the commutation relation. Changing n to n-1. Thus, we have the effects of the ladder operators on the normalized eigenstates of the number operator. The results in the yellow box is very useful in many calculations dealing with the harmonic oscillator. A reasonable question to ask would be, is there a maximum state with the highest energy that will satisfy some condition, like the one for minimum energy? That is, if you try to raise the energy of this state any further, you'll just get 0. Let's explore this condition. Again, we examine this equation in position space. And we notice this change in sign from the ground state case. Therefore, we end up not with a Gaussian function, but with an exponential with a positive exponent. This blows up as x goes to infinity, and is obviously not normalizable. So the conclusion is that there is no upper limit to the eigenvalues of the number operator. Our entire results on the number operator could be transferred to the harmonic oscillator Hamiltonian in a direct way. They simply share the same set of eigenvectors. We shall continue with the same labeling convention in the blue box. The energy eigenvalues are given by Note that the ground state energy is not zero, but equals to half of h bar omega, which is half of the energy separation. This result will turn out to be important and is often referred to as the vacuum energy in the context of quantum field theory, where particles can pop in and out of existence. Let's get back to the question of normalization. Since once the ground state is normalized, all the other eigenstates would automatically be normalized. Let's normalize the ground state. This involves integrating over the absolute square of the Gaussian wave function derived earlier, which is just a Gaussian integral. The generic solution for this is given in the green box. The ground state wave function is now normalized. Now we could derive the wave functions of the rest of the eigenstates using the equation in the green box, as well as the representation of A dagger in terms of x and p in the yellow box. Going to position space. Let's first look at the effect of A dagger on the Gaussian wave function. Reorganizing the expression in the red box a little, bringing out minus IH bar from the square brackets. We notice that the differential operator within the square brackets can be written in a more compact way. Just use the product rule to verify this, assuming that the derivative will also act on anything to the right of the Gaussian, as this is after all a differential operator. The operator in the red box is an alternative position space representation of A dagger. This generalizes directly to any powers. Let's see how this power can be evaluated. The answer is obvious by just looking at the simple case of power 2. Notice that the two terms between derivatives always cancels, leaving only the exponential functions in front and at the back. Thus all powers of the derivatives simply consolidate in the middle. Once again, we can apply this to the Gaussian wave function. We insert a Gaussian and its inverse, so that we can make a term which is the inverse of the Gaussian in front. Notice that this square bracket contains a function and not a differential operator, like the one in the blue box above. Since we are applying a differential operator, A dagger to the power of n, to a Gaussian wave function, we can simplify the term in the red box by rescaling the variable x. Define the variable z such that z squared equals m omega over h bar times x squared. In this way, the derivative z will be that of x times a constant factor. This same factor can be found above to the power of n. Thus the term in the red box takes a simple form as a function of z. Including the factor minus 1 to the power n. This is what is known as the Hermite polynomials. This is a polynomial because the derivatives bring down powers of z but preserve the Gaussian function, which cancels with its inverse in the end. Applying the expressions in the yellow and blue boxes to the eigenstates of the harmonic oscillator in the green box, we get the wave functions for these states. Thus we have all the normalized eigenfunctions of the one-dimensional harmonic oscillator. Now we can look at the parity of these functions, starting with the ground state. The relevance of the parities of energy eigenfunctions is discussed in Lecture 15. They are important to the selection rules governing atomic transitions. Check out that lecture if you are unfamiliar with this. It is obvious that the ground state wave function has even parity due to its dependence on x squared. We could see this as a relation between the inner products of the ground state and the position states. Recall that in Lecture 15, we have introduced the parity operator in order to implement the parity transformation. Because the position can be arbitrary, this equation implies the invariance of the ground state under parity. What about the parities of the excited states? We can make use of the red box, which says that applying parity twice just gives the identity, and insert two parity operators into the last expression. Here, we can make use of the invariance of the ground state. The identity in the red box can be applied repeatedly between each power of a dagger. So we end up with the transformation of a dagger raised to the power of n. We know how a dagger transforms since its definition in terms of x and p is known, and we know that x and p are odd under parity. This means a dagger is odd as well. This last term is proportional to the nth eigenfunction, with the same constant of proportionality as the initial one. This implies the following equality. Thus the parity of the nth eigenfunction is equal to minus 1 to the power of n. Of course, we can again cast this in terms of the transformation of cat n. If we look at the wave function of n again, it is obvious that the overall parity of minus 1 to the power of n can only come from the Hermite polynomial, since the Gaussian is even. Writing Hn in terms of z again, we see that these polynomials transform in exactly the same way as the eigenfunctions n. A more direct way to see this property is simply through the definition of Hn. This parity just comes from the nth derivative, since all the other functions are even. Let's work out a few examples of the Hermite polynomials using the definition in the green box. These are merely exercises in calculating derivatives. Finally, we look at how the observables of a quantum harmonic oscillator evolve in time. To do this, we only need to figure out the time evolution of the lowering operator A. When talking about the time evolution of operators, we are obviously referring to the Heisenberg's picture of time translation, as opposed to the time evolution of states, which would then be the Schrödinger's picture. If you are unfamiliar with these alternative pictures of symmetries, see Lecture 4. Thus, the operator A transforms as follows. Note that we have taken A without the time argument as the operator at the initial time, which is t equals 0. The factor of half is just a number and cancels between the time evolution operator and its inverse. We would like to shift the time evolution operator to the other side of A so that it could cancel with its inverse. Of course, this must obey the commutation rules of the ladder operators. To figure this out, we only need to evaluate the commutator of A with the number operator, since the time evolution operator is just a function of this. Using again the product rule of commutators, we have the last commutator is just 0, since any operator commutes with itself. The remaining one is just given in the yellow box. Thus, the commutator of A with the number operator is just A. This tells us what happens when we switch the ordering of the two operators. Moving A from the left of the number operator to its right just increases it by 1. The same thing happens when we move A past the time evolution operator. Which results in an exponential factor. Taking the Hermitian conjugation of this also gives us the time evolution of the raising operator A dagger. So we can see that both of these operators oscillate with the frequency omega. Thus, omega really is the frequency of the quantum harmonic oscillator, as we have previously assumed through dimensional analysis. In fact, all observables of this system oscillate with this frequency. Just consider the relation between the ladder operators and the conjugate pair x and p. Taking the difference between A and A dagger, we can express x in terms of these operators, while the sum of the ladder operators gives us p. Thus, x and p can be related to A and A dagger by these linear relations. In fact, we can consider these two sets of operators as alternative variables that describe the system. The time evolution of x and p is simply the result of the evolution of the ladder operators. In general, any function of position and momentum evolves in time in the way that is ultimately determined by the behavior in the green box. All of them oscillate with the same frequency, omega.